In this lesson, we will study two topics that are very important in calculus. One, distance between 2 points, and also local area. So, we're going to start off with distance. So, what is the distance? Well, the distance between 2 points is first we have, for example, point x, and then we also have point y. So, the distance between point x and point y is equal to the absolute value of x minus y. And since in absolute value the order here doesn't matter, then this is also equal to y minus x. So, for example, if x is equal to 1 and y is equal to 2, well then the absolute value, the distance is equal to the absolute value of x, which is 1, minus y, which is 2. And this should give us 1. And on the number line, you can see that here 1 and 2, the distance between 1 and 2 is exactly 1. So what about if y was equal to negative 1? Well, then the distance here is equal to x1 minus negative 1, which is y. And here this is equal to 2. And here on the number line, here's a 0, and this is 1 and this is negative 1. And the distance between 1 and negative 1 is exactly 2. So in calculus, we call this x minus y absolute value the distance, and we don't really want to call it the absolute value. So here we're going to see how we can get the distance of 2 points in multi-dimensions. So remember, we're working with points, and here in multi-dimensions, you're not just gonna have one single number. You're not just gonna have like x is equal to 1 and y is equal to 3, right? In 2-dimension, you're gonna have something like x is equal to ab, and let's just say that x in this case is equal to, well, we'll just give the general formula. So x is equal to a1 and b1, right? And y is equal to a2 and b2. So what is the distance between x and y? Well, this is the distance between 2 points in a 2-dimensional space. So in this case, the distance would be equal to, use the distance formula, so that's a1 minus a2 squared plus b1 minus b2 squared. And just to visualize it, we're looking at the distance between x and y. So maybe, for example, this is point x and this is point y, and we're looking at the distance between point x and y. Now here, what about 3-dimensional space? Well, 3-dimensional space, you also do the same thing, except you use the distance formula for 3-dimensionals, right? So in this case, let's just say that x is equal to a1 b1 c1 and y is equal to a1 a2 b2 c2, right? So in this case, what is the distance between x and y? Well, using the formula, you get uh, a1 minus a2 squared plus b1 minus b2 squared plus, sorry, the bracket there. Let me just write that again. Plus c1 minus c2 squared. And that's the distance. And in a 3-dimensional space, you can see here we're getting the distance between, again, 2 points. So here this can be point x and this can be point y. So point x, point y. In a 3-dimensional space, we're getting the distance between these 2 points. So now let's talk about the local area. What is the local area? So the local area is given, you can get the local area from the inequality x minus x0 smaller than ellipsin. Looks like an e is actually called ellipsin. So here, x0 is a specific point, such as, for example, x0 can be 1, or x0 can also be 2, 1, for example. And ellipsin is greater than 0. Ellipsin can be a very, very small number, such as 0.01, or 0.001, for example. And here, what is the local area? Well, the local area of this inequality here is the solution of x that satisfy the above inequality. And keep in mind that it is a set rather than just a single point, right? It can be like an interval between two numbers. That's how solving inequalities work. So let's give an example. So here, let's just say that x0. Well, actually, let's just get the general case. So in this case, how do we solve this inequality? Well, we can write this as x minus x0 is smaller than ellipsin, but it's greater than negative ellipsin. And now if you add x0 on all parts, then that's negative ellipsin plus x0. That's smaller than x. And this x is smaller than positive ellipsin plus x0. So in this case, if you were to actually look at a number line, if you use a number line, then you can see that if we put x0 in the middle and x0 is there, and here this is negative ellipsin plus x0. Here this is positive ellipsin plus 0. Well then, any value in this area satisfies any value you give to x that is within this area, this highlighted area, will satisfy this inequality. And this is actually called the local area. This is the local area. I can just draw an arrow pointing to local area. So here, the distance between x0 and negative ellipsin plus x0 is ellipsin. And the distance between x0 and positive ellipsin plus x0 is equal to ellipsin. And ellipsin can also be called the radius of the local area. You probably already see why, but it's going to be even more clear when we take a look at two-dimensional problems and three-dimensional problems. Now, as I said before, ellipsin can be greater than 0, but ellipsin cannot equal to 0. So what about in a two-dimensional case? What is the local area in a two-dimensional case? Well, in that case, x0 is a point with x and y coordinates. So, for example, x0 is equal to here AB, and the point can be, for example, 2, 1. And here on a two-dimensional grid, so here's x and here's y. Point 2, 1 is somewhere like around here, right? So 2, 1, 2, 1. And here, if we want to get the local area, that's remember, this local area is basically the solutions that satisfy this inequality. So what value of x in this case will satisfy the inequality x minus x0 absolute value is smaller than ellipsin? Well, first we have to know something. We're going to first look at this visually. So here, if we draw a distance of ellipsin from 2, 1, so this is ellipsin, this distance is ellipsin, well then here, any point that is not this point, of course, but any point before it, you're going to have a distance smaller than ellipsin, right? But remember, this isn't the only distance ellipsin can go in. It's a two-dimension, right? So ellipsin can go in this direction, right? This also has a distance of ellipsin. Now it can go in this direction. It's also ellipsin. This is also distance of ellipsin. This distance is also ellipsin. So is this one. So in this case, we'll just take one of them. Since all of the distances are equal, we just have to take one point. So let's just take this one point here. So here, we're going to get the distance between 2, 1 and this point. So while the distance is equal to x minus a squared, and a is equal to 2. So x minus 2 squared plus y minus 1 squared. And this here is smaller than ellipsin. And so what is the local area? Well, notice that, as I said before, this goes out in all directions. So eventually, you're actually just looking at a 2D circle. You're actually just looking at a 2D circle. Let me just draw that again. Okay, there we go. So the local area is actually the area inside the circle. Is actually the area inside the circle. Any point inside the circle, any point, will have a distance from 2, 1 smaller than ellipsin. Because 2, 1 to any point inside the circle is not going to reach the radius yet. And by the way, what is the radius of the circle? Well, the radius is actually just ellipsin. So that's why ellipsin can also be called the radius of the local area. Now, if you're thinking, what is the local area in a three-dimensional case? Well, in three-dimensional case, you're actually getting a sphere. Let's say that in this case, x0 was equal to a, b, c, and specifically it was equal to it's equal to 1, 3, 1. So what is the local area if ellipsin is equal to 0.1? Well, let's first see how we're supposed to use the distance formula to do this problem. So in this case, if we draw a three-dimensional space, this is point x, sorry, x-axis, y-axis, and z-axis. So 1, 3, 1 is somewhere like around here, right? 1, 3, 1. And now the ellipsin, the radius of the sphere is going to be 0.1. Now, this is not the scale. I'm just going to draw this radius a little bit larger than it should look, just so I can actually draw something that looks like a sphere. So in this case, this distance is ellipsin. So remember, this ellipsin can go out in any direction. So in this case, we'll just take this point here, take this point, and calculate the distance between 1, 3, 1 and this point right over here. So the distance in this case would be equal to here x minus a, which is 1 squared, plus y minus 3 squared, plus z minus 1 squared. This is smaller than ellipsin. So here, as I said before, you get a sphere. In this case, this sphere, so the place inside the sphere is the local area of this inequality. And you can probably see why. Any point in the sphere is actually going to have a distance from 1, 3, 1 smaller than the distance of ellipsin, right? And the radius of the sphere is, the radius of the sphere is exactly ellipsin.